Well, welcome to the book the third recording of Quadrivic Mathematics with Daniel Jones and Chris Garcia. I'm going to turn it over to you, Mr. Jones.
Okay. Thank you, Kathy. Again, thank you for your time. Thank you for those who are watching these videos. It's exciting making these videos. This is the product of a lot of research, a lot of time, obviously, a lot of trial and error. What I like to tell people is that this is the product of listening to my students. I basically would pose questions to my students, oftentimes questions I didn't have the answers to. Like I remember one time I was sitting there, what is the answer to this question? I knew what I'll do. I'll just ask my students. And it seems to always work out because listening to your students is a good way to learn yourself, as teachers know. So this is our third video. It's on book the third. So in this series so far, we've covered two books. The first book was on sets and predicates. The second was on relations and relationships. And like we talked about before, those two books serve as the foundation for all of mathematics. 100%, no matter what math field you're studying, you have to start with sets and relationships because that's what mathematics essentially studies. Again, the goal for this project is to show how mathematics can be really rooted and grounded and linked to language. There's a lot of reasons for that. One of them is, Chris and I were talking before the video, why we do that. Because if you link it to language, it's a good way to test to see if things actually make sense. It's easy to scribble some symbols on the board or on your table and think you're doing something, on your paper, think you're doing something. But my belief is if you can't actually put it into a sentence, you probably don't really know what you're doing. Don't really know what you're doing, especially if you have a self-consistent system of language by which to describe things. That makes everything cross-check itself. It becomes a self-correcting system, which is what you want for any system. Consistency is the objective. And as we've talked about before, this entire work is broken into two series. There's a series on arithmetic and a series on, I should say, two volumes, two series, arithmetic and series on geometry. So far, we're just doing arithmetic. Arithmetic is all about the how many. This is the big idea, right? And the geometry is all about the how much. Okay, and that is exactly how the ancients saw arithmetic and geometry. So these things, these ideas are not new. What we're really doing is applying the knowledge of modern mathematics to this ancient system to kind of bridge modern mathematics with ancient mathematics. It has an ancient feel with all the modern wisdom and understanding. So it's the best of both worlds, really, and that's why we call it quadrivic mathematics. Now, I want to start tonight by reading a little bit from one of my favorite authors. His name is Nichomachus of Gerasa, 100 AD, from Greece. He understood it. He got it. He wrote this fantastic book called the Foundations. I think it's called the Foundations of Arithmetic. Sorry, Introduction to Arithmetic. It's very difficult to understand because it's an ancient text and their mathematics was really good. But he really spells some things out that I think we need to hear. And it lends itself into book the third today. Kind of gives some background as to why we're doing this with arithmetic. The first quote I want to say, there's a lot of really good quotes here, is this one. He says, lost my page, where'd it go? Okay. He says, things. He starts the sentence with things. When he says things, he means anything. Kind of like our work, where book the first, like an empty set is that which contains nothing, no thing, right? So he says things then, both those properly so called and those that simply have the name, are some of them unified and continuous. Some things are unified and continuous. For example, he says, an animal, the universe, a tree, and the like. Those things are unified and continuous, which are properly and peculiarly called magnitudes. Okay? I wouldn't say that they are magnitudes. Modern math wouldn't say that, wouldn't allow that. And I think this is some of the confusion in a lot of ancient texts. They confused the thing with the set that describes the thing. Okay? And we're going to talk about that today. They're called magnitudes because those are things that you can measure. For example, the animal, you could talk about how much it weighs, right? It's one thing talking about what you can measure with, its size, its weight. So those are measured in magnitudes. The others are discontinuous in a side-by-side arrangement, he says, and as it were, in heaps, which are called multitudes. So even as in this ancient text, he distinguishes between magnitudes and multitudes. Magnitudes being how much of a magnitude, and multitudes being how many. His examples are a flock, for instance, a people, a heap, a chorus, and the like. Then he says, wisdom then must be considered the knowledge of these two forms. I don't want to get too much into the philosophy here, but there's something to be said about what he says even in that statement. The fact that wisdom in his mind is the knowledge of these two forms. Why? Well, it comes back to what Chris Garcia was saying on day one, right? Because when we're studying mathematics this way, we're actually looking at reality, the things around us, and how we can study them. You can't even study them unless you can talk about how much of it you have or how many of them you have, the singularity and the plurality, which is magnitude and multitude. Okay? So the ancients understood that geometry was magnitude and arithmetic was multitude. Okay? The second quote I'm going to read later in the text, he says, if geometry exists, arithmetic must also needs be implied. For it is with the help of this latter that we can speak of triangle, quadrilateral, octahedron, icosahedron, double, eightfold, 1.5 times, or anything else of the sort which is used by a term in geometry. And such things cannot be conceived of without the numbers that are implied with each one. What he's saying is that, and he uses these words, if you abolish arithmetic, if arithmetic just disappears, geometry must also disappear. Because without arithmetic, you can't say triangle because triangle implies 3 sides. So geometry implies that arithmetic exists. Setting the foundation for arithmetic first, then geometry, which is completely foreign to modern mathematics that puts everything into one big lump and says, this is just math. It's called integrated math. And there's no distinction between the how many and the how much, contrary to how our brains are wired to think, which is why modern math cannot describe reality. And modern math cannot define their terms. You look into a modern textbook, 7th grade math textbook, you think you can find a definition of an integer. No textbook defines an integer. They just say integers do this, but they don't tell you what an integer is. Just because they can't define their terms, and it's so sad. But we're happy because we can define our terms. So here we are. That's what we're going to do. Book the third sets the stage. Integers is not until book 5. We're currently on book 3 because integers can't be defined unless you know what a number is. And numbers is really the essence of what we're getting at when we say the word multitude. It's the how many. So today we're going to talk about the how many. We're going to define the how many. We're going to define multitude. So everything has a definition. But again, all these definitions stem from books 1 and 2. So it's very sequential. Like if you're watching a really good movie series and you start right in the middle, you're like, what the heck is this? Like Star Wars just started with A New Hope. What the heck is Endor? Where does that come from? Like you have to go back and watch the previous movies and suddenly everything makes sense. So that's kind of how these things are arranged. Everything has a place, everything has a definition, and it all comes back to language. Let's do it. Let's dive in. I'll read from book 3. Chris, if you want to say something right now, before we get started, this is a good time. Other than that, I'm going to get up book 3 and start reading and let you describe as we go. Anything you want to say?
I think you got us off to a pretty strong start.
Okay, well, let's do it. Here we go. This is the text. It reads, Book the Third. Let the following be defined. First, 2 sets are said to be equinumerous. You just full screen me away from my reading.
Oops.
Let me view. There we go. Okay. First, 2 sets are said to be equinumerous. If all the elements of one are paired with all the elements of the other with an unus ad unum relationship. That's our first definition.
Okay. So we're probably going to want to backtrack just a little bit and refresh our minds on what the unus ad unum relationship is. So that comes in at the tail end of book 2. It's the 8th definition. A relationship is said to be, or was it 6th? I had it and then I moved off from it.
It's right there. It's eighth, but it's the last phrase in the eighth definition.
Relationship is said to be ad unum if all the outputs for any given input are the same. E unum if all the inputs for any given output are the same, and unus ad unum if both. So it's basically a one-to-one relationship is what it literally translates to. And just as a refresher, our domain, object, secundus, our range, primus, subject, from before with the relationships being formed. So we had like the bigger than was our example here between Jupiter and Mars, where we had the examples of the domains where being bigger than. So Jupiter is bigger than Mars. A dog is bigger than a mouse. A cow is bigger than a rat. And so for a one-to-one relationship, there's this pairing off happening. And the reason we care about that is because we are then able to speak about things being equinumerous on the basis of this pairing off happening. So for the pig set, and
Let me jump in real quick, Chris.
go ahead.
Yeah, so what he said there was pretty profound. We're basing the idea of equinumerosity on the idea of relationships because we want to eventually define what a number is. It's very easy to define, but we can't use a word in its own definition. We can't say a number is, well, it's a quantity or something like that, because what's a quantity? But using the idea of relationships allows us to have a foundation by which a language by which we can define what quantity actually is. That's what Chris is getting at here. So two sets would be equinumerous if all the sets of one are paired with all the elements of one are paired with all the elements of the other with an unus ad unum relationship. So there, Chris is giving us an example of an unus ad unum relationship between two sets, thus establishing that those two sets are indeed equinumerous. Kathy, does that make sense to you so far?
Yes. Yes, it does.
Okay.
Okay. I think we go on to the second one.
You can think of it as just like drawing a line between each, like if there's one there, there's for every one in one set, there's another one in the other set, and vice versa. There's a correspondence all the way through. They're equinumerous. In other words, they're equal in number without saying the word number.
All the way down the line.
Yeah. Okay, so we established that.
It's pretty intuitive. It
Okay.
just has taken a bit of groundwork to be able to articulate in our system.
That's true. The hard work has been done.
I can just paste in the second. So second, do you want to keep reading or do you want me to take
Oh yeah, I'll
the
go.
reading? Okay.
The multitude of a set is the set that describes all sets equinumerous with it. Multitudes formed by equinumerous sets are said to be equal.
Okay. So I'll go ahead and pull some of the examples that we have.
The multitude of a set is the set that describes all sets equinumerous with it. Just to give a little bit of history, this definition did not appear anywhere until the 19th century by Gottlieb Frege, I think it is. And you can see why no one came up with it. because it's kind of wordy. It's very unintuitive, right? But this really is what a multitude is.
And then something I'll point out as well. So we have this describes language again, which we're grounded in reality. So going all the way back to book one, with descriptions. A set is the extension of some predicate. The subjects of a predicate are said to be the elements of the set formed by it, and the set is thus said to describe its elements. So the description relation is between the set and its elements. And so one thing we want to point out here is that a multitude is the set that describes all sets equinumerous with it. And so it's not describing the elements of those sets, because the elements of the multitude, which is a set, are other sets. So the set is the element here, not the elements of those sets, if that makes sense. And so that'll, I guess, with these examples, right? So the multitude of set A, we're calling lowercase a. And so this multitude set, lowercase a, would be the set that describes all sets equinumerous with the set uppercase A. So if a set is equinumerous with this set here, this uppercase A set, then we would say it is described by the multitude of set uppercase A, lowercase a. And so that applies to these other sets. And so the distinction I'm pointing out is.
And by the way, sets A, B, and C are equinumerous. That's kind of the point here. A is an octad. We're going to learn that language later. An octad is a set of 8 things, which we haven't defined any of those terms yet. But you can think of set A as an octad, think of set B as an octad, think of set C as an octad, even without saying the word octad. If you don't even know how to count, you can see those sets are equinumerous. Even an animal can probably tell that those sets are equinumerous, because there's a one-to-one correspondence you can make between them. Kathy, does that make sense? Why they're equinumerous?
Yep.
Because you can just draw the line between them. And so when we say the multitude of set A is A, that lowercase a, like Chris said, is the set that describes A and B and C, capital A, B, and C. So I would say the set lowercase a, another word for that would be being an octad. Being an octad describes A. Being an octad describes B. Being an octad describes C. Therefore, being an octad is the multitude of A, B, and C.
So it's this, right? Where the sets are the elements. It's not this.
There we go.
So being an octad set does not subsume these sets that are octads. It describes them. And so the sets themselves are the elements of the being an octad set. Does that make sense?
Because being an octad doesn't describe that yellow thing. It describes the entire set. And that level of abstraction is the reason why it took mathematicians so long to figure this out. 19th century, so recent, just to get this one definition down. That's why we have the advantage of modern mathematics, which is amazing. Like, we're looking at things classically with a modern advantage.
So yeah, I point this out because I was struggling with this conceptually. And it made some of the definitions later on a little confusing. But with this in mind, I think the third definition should be pretty straightforward.
Kathy, do you want to say anything to this?
I think I'm tracking.
Okay.
I guess I'll actually say real quick, this is what, like, I'm like about to blow right past it, but this is like one of my favorite parts to point out, just kind of along the lines of this sort of pattern that starts emerging of like repeated abstraction, where we abstract and abstract and abstract, and it's kind of like this fractal where we are able to deal with like less and less tangible concepts, but it perfectly mirrors the way we do interact with reality, the way we come to understand what a thing is and assign words and meanings to concepts and ideas and things that we see in the real world. And so the idea of a multitude, I think, captures that really well, where we are kind of pulling out this idea of something having a count of eight. And the idea of something having a count of eight sort of emerges from the pattern of seeing a collection of things that have a count of eight. And so our understanding of what it means for something to have a count of eight emerges from observing many things that have a count of eight and realizing that they have something in common, right? Like you get enough of these things together, and what you realize is what they have in common isn't their color, isn't their size, isn't their mass or their volume. It's how many of them there are. That understanding of how many of them there are emerges like just like the color blue. You know, you have a lot of different things that are blue. The idea of blue emerges when you throw enough things together in a set where the only thing that's in common to all of them is that they're blue, that there are eight of them, that there are two of them. And so the multitude emerges because it's the only common kind of denominator, the only common descriptor for these things with a big enough set. That's just kind of how that's how I imagine kind of I came to learn what it means for these things to be. I think that's the model that people learn these sorts of concepts from. And I think this definition of a multitude captures that really well.
Yeah, it's the heart and soul of a mathematician right there. Being able to abstract the idea of what something is by looking at enough examples, right? Exactly like you said, Chris, you said so well. Eightness, right? Being an octad. The number eight is, by definition, being an octad. That's what we mean when we say eight. That's eight because it is an octad. Good. Excellent. Let's keep going.
All right.
All right. Are we on third?
Yes.
Okay. Third, the sum of the respective multitudes of two disjoint sets is the multitude formed by their union. If one multitude is the sum of two others, then each of the two is said to be the difference of the sum and the other. So the word sum, I think everybody knows the word sum means to add. The word difference means to subtract. Guess what? We are defining actual addition and subtraction. The things that we do as children, we're giving a definition to it right now in this definition. Something we all know, but don't know that we know.
Okay. So I'll pull in once again some of the examples we have.
We're putting words to things that we experience every day is what we're doing, putting words to it. Yeah. So there Chris has two sets, set A with a multitude of lowercase a, and set B with a multitude of lowercase b. What you going to do those two sets, Chris?
We're going to take the union of each of those disjoint sets, which we can then, from that union, form a new multitude. And this multitude is said to be the sum of the multitudes of set A and set B.
Now notice Chris's use of the word multitude. I'm sorry, use of the word union. Again, it's drawing back from book one. Again, why we need to have all these books in sequence, because everything has to be defined. You can't just throw in a word there that hasn't been defined yet. So he's using the word union because we know what it is. The union of two sets is a set that describes the elements of either. That's how we defined it in book one.
And the reason we need to construct the sum from these two disjoint sets, So A set and B set, and not just the union of the multitudes, which are themselves sets, is because, to come back to the being an octet, the union of the being an octet multitude and the being an octet multitude is still the being an octet multitude. But if you were to take the union of two octads that were disjoint, you would then have a set with a count of 16. And the multitude formed by that set would be the multitude. I don't know the word for it. Having a count of 16.
Yeah, we actually have words for all these in a document that I've been teaching my seventh graders, but I can't remember what it is. I think it's called because one is a dodecad,
Yes,
so it'll
I think
be a hexadecad, I think. Hexadecad
that
would be
sounds
a
right.
16 hexadecad. Yeah.
Yeah. So that's why we do the two sets, join them, and then create the multitude.
So yeah, the multitude of C is, so what we're saying here is that lowercase a plus lowercase b equals lowercase c. That's the notation for that. That's what we learned in like first grade or whatever, whenever we learned that, right? A plus B equals C because the union of A and B is C.
Can I ask a question?
Yes.
When you say two disjoint sets, what does disjoint, what is the definition of disjoint?
I can't do word search on this, but I have the old document on. Was that in book the second?
Book first. I can find it if you just zoom in a little bit. It's going to be under intersection. Go down a little bit. Right there it says, eighth, two sets are said to intersect. Eighth, right down here with the, yeah.
I see.
Two sets are said to intersect if they have a common element. And the common element is thus said to join them. So even though I didn't define disjoint, by implication, disjoint means to be non-joined. So unjoined, which means the two sets do not intersect. So in this context, the yellow and the blue sets that Chris have for sets A and B, if those sets are disjoint, and that is a modern math term, we're saying that they don't have any elements in common. And the reason that's important in this definition is because if you have two sets that are joined, then their union won't make the sum.
So if B had 5 yellow shapes, they would be joined?
No, it's more like this.
They
Chris,
would
can
be
you come?
equinumerous, but not joined.
Do you want to be back on book one?
No, that's a good example right there. Can you
So
explain how that would not define the sum of two sets?
yeah, so since these two are joined, right, the count of being a triangle is 3, and the count of being green in this case is also 3. So the union of those two sets would only, but since they're joint, the union of these two sets only has 4 elements.
So therefore, 3 plus 3 equals 4, right? Which is false, right?
Mm-hmm.
So the condition is that the union is the sum if the two sets are disjoint
Okay, so they have to be disjoint.
by definition.
So being blue, being so this is going to give us what we want by comparison.
Good, good.
So this is going to be 5, and that's going to be 3, which will give us a count of 8 when they're joined because there's no repeats essentially.
Okay.
Yeah, each
Thank
of
you.
these being intersection. Yeah. Good.
Yeah, I think it's pretty clear. So basically, this is how we count. This is how we add things anyway. We've got these blocks. We got these blocks. What's their sum? Put them together. And it's exactly what you do in kindergarten to add two numbers. You take two sets with those numbers, put them together into a union, and count how many you have at that point. And that's the sum of the sum of the multitudes of the two sets.
Okay, I have another question. I'll try not
Sure.
to, as
Yeah.
I'm trying to understand this. So is that correct that B could not be blue diamonds? If there were blue diamonds, they'd be a part of set A.
Yeah.
Yeah. If this was, yeah, being blue and this was, so here I'll do another.
Oh,
So
yeah, that's right. Yeah, being blue diamonds, right?
well, if this was just being diamonds,
Oh, that would be problematic too. Yeah.
then this would also be, we would end up with this,
Mm.
which would give us 10.
Which gives us 5.
Right. That's right. There we go. Yeah.
And 5 plus 5 is not 5.
Yeah. So we're just articulating a way for us to make sure that there's no repeats when we're trying to we already know what we want the sum to be and to mean. We're just articulating a way and rules to make sure that you can construct those sums, even if you don't already know what it should be.
Basically, we're defining our terms. We're defining addition. Yeah.
I just want to make sure I understand the definitions of terms.
Yep.
Yeah, these are great questions.
Yeah. Please ask away, Kathy. I mean, I already miss Bill because he was filling in a lot, and Dale too. Just the more voices, the more questions, the more conversation, the more fun this is. So, yeah, ask away.
Yeah. We want to move on to,
Oh
I
yeah,
think we're
let's
on
go.
fourth now.
Yeah. Okay. I think I have the same one you do. Okay. Fourth, a monad is a non-empty set for which all of its elements are the same. A dyad is the union of two disjoint monads. A triad is the union of three disjoint monads, etc. So the first one says a monad is a non-empty set for which all of its elements are the same. Let me talk about this one. So it's very tempting to want to say a monad is a set with just one thing in it. But alas, we haven't defined one yet. And we have to define our terms. But we have the language by which to define a monad without using the word one, because we defined sameness in book 1. Let's suppose I have a set that has, it says being Mr. Jones, okay? Being Mr. Jones. And then let's say that all its elements are the same. Let's say in that set, how do I put this? Okay, sorry, I do it this way. Let's say I have a set with just Mr. Jones in it, okay? We want to define that as a monad. It's a monad if all of its elements are the same, which means the person in that set has to be in every set. I can't totally fast how to say this. Let's go back to the definition. Two things are said to be the same if each is an element of every set that the other is also an element of, okay? So for example, Mr. Jones and the man talking right now are the same because no matter how you describe Mr. Jones, everything that you can say about Mr. Jones, you can also say about the person who's talking right now. Okay, so that's what it means for them to be the same. And so if all the elements in a set are the same in that sense, that means there's only one thing in the set. That's what it means for it to be a monad. I probably butchered that.
I think something that comes to mind is like different names for the same thing or the same individual,
Yeah.
same unique thing.
Yeah.
Like
If everything in one set is the same in every way, then that means all those things are just one and the same. So there's one thing in it. So we're basically defining what it means for a set to be a monad without using the word one. Did that make sense to either of you guys?
Mhm.
Okay.
I guess it's pretty tough to think of actual examples. Like we know it to be true. It's just it's kind of tough to think of a really solid example on the spot. I guess like how to frame the wording of the set to where it has just the one element, but like many different ways, I guess, to kind of describe that same element.
I suppose we have to come up with an actual monad. The
Yeah.
Pope, being the Pope. There we go. Being the Pope is a monad. There we go. Because there's only one Pope, right? So being the Pope is a monad because all the elements in that set are the same, right? You can call it different things. I don't know what the Pope's name is right now, but you can call him the Pope. You can call him, what's his name? Do you guys know?
Pope Leo the
Pope Leo. Let's just say Pope Leo,
54th.
okay? So you can call him being Leo. You can call him being the Pope. It doesn't matter what you call him. It's always the same person. Therefore, being the Pope is a monad. Anything that can be
So
said of Leo can also be said of the Pope, etc.
yeah, so you would have like the Pope, you would have Leo, you would have, I don't know,
There we
his
go. That's
mom's nickname for it, or even just these two, um, where you can put them both in here as two different elements, but really they are the same.
yeah, because there's only one Pope. Okay, we don't need to belabor that one. Okay, so that's what it means. That's what we mean by a monad. Then a dyad is the union of two disjoint monads. So take a monad, take another monad, assuming those two monads are disjoint. If we take their union, you now have a dyad.
Oh, there's probably an example in the book. I'll just pull this. This being a monad. And then we'll say this is another monad.
By the way, just to clarify, the thing isn't the monad. The set that describes the thing is a monad. So in that case, that's a dyad. It's the set that describes the two monads. Sorry, it's the union of the two monads. I just did it myself.
Because
So
this is coming back to the same thing we had up here, right?
yeah,
Yeah. So it's the union of two of these, not the union of two of these.
yeah.
So this represents this. So actually, probably something that would be helpful to do is, well, sorry, this is being an octad. So this should be everything that's an octad.
I think if you put a circle around the monad, two circles, one around each monad, you'll have two actual monads. There you go. And then the union of those two is the bigger circle. That's the dyad. There we go. So dyad is the union of two disjoint monads. Yeah, there we go.
Okay, I think I actually misspoke then, right? So we're talking about two of these.
Yes.
Yeah, because this is not a multitude. This is just straight up a set that has one element and
Right.
another set that has one element. And so this is just nomenclature to very quickly call out the count of the set. So instead of saying that's a set that has only one element in it, or yeah, a set where all the elements are the same, you just call it a monad.
Yeah.
Dyad is two of those.
Yeah. So much easier to say than the set in which all the elements are the same. It's just a monad.
Yeah.
Good.
So that was fourth.
That was fourth. Okay.
And we, of course, want them to be disjoint because then we run into the same problem as before with repeat counts. Disjoint avoids that.
Okay. Fifth, naught is the multitude of an empty set. One is the multitude of a monad. Two is the multitude of a dyad, etc. We just defined naught, one, two, etc. So history in the making, we now have a definition for things that we all know, numbers, things that we can count. 1, 2, 3, 4. Like, what are those things? Again, this seems intuitive, and it is. And it seems obvious and basic. But mathematicians, it took them so long to figure this out. They were just tripped over it for so long. And there's books and books and books of people attempting to define these things. Gottlieb Frege, end of the 19th century, said, no, it's this. And that's what we're defining. So he defined what we mean by one. It's the multitude of a monad. Two is the multitude of a dyad, etc. Which is what we know to be true, right? Because if I can keep talking, remember what a multitude is. A multitude is that which is the set that describes all sets equinumerous with it. So the multitude of the pig set, for example, is being a triad. But also the multitude of the pig set is 3, because 3 describes the pig set in the same way that being a triad describes the pig set. Therefore, 3 by definition is being a triad, or in other words, the multitude of a triad. Did that make sense? Getting back to our language again, right?
Yeah. And we've got a bunch of these. I'll paste them all in at once.
Go for it. Do you want to expound on that pig set analogy, Chris?
I guess the definition of the multitude really gets to the heart of it, where it's the equinumerosity that is really informing what we mean when we say like the number 1, 2, or 3. So what were the other other than the pig, what were the other?
I would say the pig set, the stooge set, and the musketeer set. Those are all triads. So they're described by being a triad, or they're described by the number 3, because there's 3 pigs, there's 3 stooges, there's 3 musketeers. So again,
Yeah.
3 describes each of those sets in the same way that being a triad describes each of those sets. Therefore, 3 is the multitude of a triad, or just simply, quote unquote, being a triad. That's what the number 3 is, being a triad. It describes a triad.
It's that element, it's that common thread that we're isolating
Yeah.
and kind of then being able to apply to things once we've kind of extracted it or like abstracted it. Once we've gotten to the essence of 3, we can now use 3 to describe things that
That's right.
wouldn't have made sense without that context.
Again, defining our terms. Everything is defined in this system, right? Every single thing. Kathy, any questions on that?
Yes. So as I'm looking at the example, I'm wrestling with my mind that in the 4th definition, it says a dyad is the union of 2 disjoint monads. And then as I look at the 5th one, I look at the dyad and I see the 2 red hearts and I don't see a disjoint. And I'm wondering if there's a difference in the word for dyad. Are those 2 red hearts joined?
So we would say we would do it like this. And so this would be a monad. We would say we have,
So, you know,
we'll
like
say
the
these
Venn
represent
diagram,
actual hearts.
they'd both be in the center.
Um, oh, I see what you're saying. So let's just pretend that these represent actual hearts. And so we'll say we have being Chris's heart and being Kathy's heart as our two sets. So each of these sets would be a monad. Oops. So I guess this right here would be a crude sketch of this being more fleshed out, where we have the set being Kathy's heart and the set being Chris's heart. And they're disjoint because we each have two separate physically like beating hearts in our chests. And so the set being Chris's heart is a monad because it only has one element, or all of its elements are the same, right? Being Chris's heart, where you say, this is my heart, or this is my organ that circulates blood in my body, or
I understand the difference of the
yeah.
hearts. I think it's the
Sorry, I'm connecting back to the monad. I was like, oh, here's an example of a monad where we can call the heart different things. Um, so yeah, the union of these two sets then. So if we take the union of them, the union is a dyad. Because the union has now two elements, which is what this is showing. So this circle then is basically this box.
Yeah, the Venn diagram drawing is a lot more common in logic, whereas the other drawing, the one Chris drew above, that's more common in arithmetic. So you kind of have to show both because the Venn diagram one is more continuous in nature. The other one's more discrete in nature, where you're counting things.
yeah.
Yeah.
I think I'm just trying to understand the word dyad, what it means, um, based on the examples.
This right here is a dyad. The set that describes these two objects is a dyad,
Mhm.
where each of these objects is an element of that set. So this would be whatever definition this is. So being an object in the subject example. And this set has the two elements, one being the blue pentagon, one being the red pentagon that is smaller. We would say that this set is a dyad because it has two elements.
And that makes sense because there's differences. There is a difference. Well, no, okay, now I shouldn't use the word difference, but the element,
No,
there's a,
I got you, Kathy.
yeah.
Yeah. So that's actually a good point. It kind of comes back to what we're thinking of, what we're thinking of when we're thinking about what it means for two things to be the same.
Mhm.
Because on paper, you can draw a heart and you can draw the heart again and be referring to the same heart, even though they're two different drawings.
Mhm.
Right.
So abstractedly thinking, you have to determine, what is different and what is the same. So that's why Chris spelled it out. Like if this is Chris's heart and this is Kathy's heart, those are two different hearts. But
Right.
Kathy's right. In our examples, we're kind of mixing metaphors a lot. We oftentimes have heart and then heart, but we refer to the same heart. So I think
Yeah.
context has to determine, Kathy, whether or not two things on paper are the same.
Okay.
Yeah. I want to point something else out. In the definition 4, it says a monad is a non-empty set for which all its elements are the same. Then it says a dyad is the union of two disjoint monads. A critic could easily say, hey, look, you used the word two before defining the word two in the next definition. But two in that sense, in the fourth definition, when they say a dyad is the union of two disjoint monads, we're not counting the number of monads. What we're doing is saying it's the dyad of a monad and a monad. In that sense, when we say there's two monads, we're saying there's a monad and a monad. So probably, if I want to be really precise, I would say a dyad is the union of a monad and a monad, just listed twice. And then a triad is the union of a monad and a monad and a monad. But saying three monads is just a short way in English of saying a monad and a monad and a monad.
Yeah.
Would you say a triad is the union of a dyad and a monad?
You could. Yes. There are two different ways to define it. You could go one way or the other. Yeah. I did it this way because it's actually easier to say. Because otherwise you have to say the dyad and the monad being disjoint. You can just say as an adjective, three disjoint monads. It's actually faster this way. But yeah,
Right,
you could
but you bring
easily.
up a good point that you haven't defined those two
Yeah.
and three yet. So.
Yeah. So for people watching this and they can't ask that question, I just answered that question, right? The reason the word two is there because I'm saying it's a union of a monad and a monad.
Yeah.
Which is
So
probably what I should do. Probably should just say it's a monad, just to avoid that problem.
this is more what we usually do, like without the shapes, where it's just the dots and then what the dot represents. And so typically you would say that if the dots are different, they're distinct elements, which again, back here, we could kind of be contradicting ourselves where this being the Pope set, you have the Pope and you have Leo, but really these are
There you go.
the same. So
Yeah.
this is kind of this is what we were trying to convey, I think, earlier by the
Yeah.
sameness.
Yeah. There you go. That's
Technically,
even though the Pope and Leo are both in the set, it's still a monad. There we go.
yeah. And so being on this call or being a person on this call is a triad. The elements of that triad set are us three.
Even if you give Daniel another name like Jones, like we did for Leo and the Pope, it's still a triad, even though Jones and Daniel and Kathy and Chris are all on the call. How is that not a tetrad? Well, because some of those are the same, which is what we do in our natural language too.
Yeah. And then again, right, this triad, its multitude is three. The multitude three does not describe each one of us individual elements. And that's coming back to this concept here, right? The triad three wouldn't describe the individual elements, it describes the sets. So the multitude three would describe this set of three people. And right alongside this would be the Stooges and the pig sets. Or the Stooge set, rather. And then all that updated.
Should I keep going?
Yeah.
Okay, again, this definition was given to us by actually Bertrand Russell, who I think he was building off of Frege's work. He says, I guess he doesn't say exactly this, but sixth, a number is one or the sum of one and a number. A polyad is a set whose multitude is a number. So let me read the first one again. A number is one or the sum of one and a number.
So just from a basic understanding, when I read that definition, I think that number is one or two because it's the sum of one and a number. And if number is one, then the biggest it can get is two.
Exactly. So the only numbers we have are one and two.
Yeah.
But a number is also the sum of one and a number. But you just said that two is a number, right? So therefore, the sum of one and two also has to be a number,
So but a number is either one.
or the sum of one and a number.
But if a number is always one, then the
It's
sum of
Then
one
one and a
or.
number is two.
therefore two is a number. You agree that two is a number, right? By that definition, a number is one or the sum of one and a number. Since one is a number, one plus one is a number, right?
Yep.
Therefore, two is a number. Two is a number. But a number is one or the sum of one and a number. If two is a number, then the sum of one and two is a number, which means three is a number. Do you agree?
I think so. I just when I just first read it, it just comes off as if number is one, or the sum of one and a number. So far, the number is only one. Two has not been introduced. I guess that's what I'm saying.
Well, it is if you say that a number is one is the sum of one and a number, and one is a number, right?
Have you already established that the multitudes are numbers?
Nope. Nope. This is the first time the word number shows up.
Okay, so where do you get two in regards to number?
Take it away, Chris. Where do we get two from?
One and one. I think it's just above, right? Or is that still? So right here, yeah. So not is what we call the multitude of an empty set. One is what we call the multitude of a monad. Two is what we call the multitude of a dyad. So on and so forth. So when we say one, what we're talking about is the multitude of any given monad. And so when we take the sum, which we talked about earlier, right, is these two disjoint sets, taking the union of them, and then we get the multitude formed by that union. So if we were to come back to this example, so this monad, disjoint monads, take the union of them, we get a dyad. The multitude of this dyad is two.
And that makes sense. I was just wondering where number and multitude were connected.
So two would be, okay, so a number is one or the sum of one and a number. So the multitude of being the Pope would be what we call one. And so if we do this process, this is showing 1 + 1 essentially, how we do 1 + 1, which would give us 2. So we now have the number 1 and the number 2 from this.
Is it fair
And
to say that there is an assumption that multitude is connected to number just based on the term one?
yes,
Is that what I'm missing? Okay.
1 is the label for the multitude of a monad.
So you could say the number is the multitude of a monad, or the sum of the multitude of a monad, and a monad.
Yeah, like if you wanted to substitute in the definition, if you wanted to substitute, yeah. So we could say a number is the multitude of a monad or the sum of the multitude of a monad and
And a number.
yeah.
You have to leave that one because that's defined in the first part of the phrase.
Okay, that's helpful. Thank you.
Yeah. So yeah, it just chains on because once we get two is now an eligible number. We do 1 and 2, that gives us 3. You do 3 and 1, 4 and 1, 5 and 1, and you can just make every number from there.
This definition, I was telling Chris this earlier, in every modern textbook I've ever seen, is a postulate or an axiom. It's called the principle of induction. Bertrand Russell is the only person I found that says, no, 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 no. It's not a postulate, it's a definition. Because his philosophy is if you can define something, you should. If you don't, if you're just postulating things, his phrasing is, well, then you're involved in thievery as opposed to honest labor. And I agree with him. If you can define something, you should define it as opposed to postulating it, because otherwise you're avoiding defining your terms.
Yeah.
And so he says, this isn't a postulate after all, it's a definition. This is what a number is. That way, when you prove something true for a number and the sum of one and a number, you've therefore proven it true for all numbers because that's what a number is by definition. And this principle of induction is very famous. It's very widespread. Everybody in the math world uses it. I just don't know if people realize that it's a definition. It's a definition of what a number is. And that's what we're establishing again. We're establishing what are these things that we're working with. So when we prove things about numbers, we're proving it's true for all numbers by definition. And then a polyad is a set whose multitude is a number. So octad is a polyad because its multitude is a number, namely 8. Ennead, I think, is how we call, or is it nonad? I can't remember now. Is a polyad with 9 elements in it, etc., etc., etc. Yeah.
I remember when you were introducing me to the arithmetic volume, I I was taken by surprise how quickly you got to the definition of a number. Because in geometry, it's like
Yeah. Yeah.
much further down the road.
Yeah. It's not till book like 10 and 11 that you start
Oh, wow.
seeing quantities. Yeah.
It made me think that, something must have been missed or like it was oversimplified. But continuing to study it, I've seen that its simplicity is its power.
Yeah. Okay, we've got 4 definitions left. Hang in there, folks. Definition 7. Here we go. If one number is the sum of 2 others, then each of the 2 is said to be less than the sum, and the sum is thus said to be greater than each of the 2. So, for example, since 5 is the sum of 2 and 3, 2 and 3 are both said to be less than 5, and 5 is greater than 2 or 3. Now, notice that this definition would fail if we included 0 as a number. There are ways to include 0 as a number if you really wanted to find 0 as a number. But the definitions are simpler this way, and plus this reflects how things were done classically. 0 was never considered to be an actual number until very recently. But I won't quibble over that. If people would rather define things differently, they can. Because some textbooks really want 0 to be a number, and that's fine. But as I have it set up right now, the first number is 1, which makes sense because that's what we tell preschool children. The first number is 1. So it is actually very intuitive. And having 0 as a number actually isn't necessary. And yeah, good.
I think it's more intuitive to have 1 be the first number because when we are learning what it means, or like when we're starting to learn what it means for something to have a count, to be numbered.
Yeah.
I feel like you don't really you learn what it means for there to be 1 of something before you would learn what it means for something to have not,
Yeah, and also don't forget that this isn't saying that not doesn't exist. Because if you look up, the word not's already defined. Not is just the multitude of an empty set. We just don't call it a number. It's a multitude, but it's a multitude that's not a number. Just like infinity is also a multitude. That's also not a number, even though it's a multitude. Should I keep going? Okay. Eighth, the product of two numbers, a first and a second, is the sum of the first seconds, which is a very strange definition. If one number is the product of two others, then each of the two is said to be the quotient of the product and the other. So what that's trying to say is the product of two numbers, a first and second, is the sum of the first seconds. Chris, what does that mean?
So I was having a tough time with this earlier. So I'll take our example we have here in the book for 5 and 3. So what that's saying is for the first and the second, if the first is 5 and the second is 3, each of the two's all right. Product two numbers, first and second, sum of the first of the second. What was this updated to? Or is
There's
this right?
I can't decide what the best way to say it. What I have written right now in the books is the sum of the first seconds or the sum of the first of the second. Either
Yeah.
way,
So
yeah.
I this sum of codes me to have, the sum of X and Y. And so it was throwing me that we didn't have and, we had of the second. But this is this saying like that there are 5 threes. So it's the sum of the first 5 of the second threes. So it's saying we're having 5 3 times. Or
Three
if you,
five times. If there's 5 threes, that would be 3 5 times.
yes,
Yeah.
yeah. So the wording's a little tricky, but the concept is, I mean,
That's what multiplication is. And that's where we get our word times. That's why we say 5 times 3. When we say 5 times 3, we're saying 3 5 times. You're adding 3 to itself 5 times, or 3 5s, or 5 3s, I should say, 5 3s. We're trying to say the first of the second, the 3 5s, the first number of the second is what we're trying to say in that definition.
yeah, it's tricky because maybe times is the best word to include in this type of a
Maybe,
definition, but
maybe.
it's got such a heavy connotation with
Yeah.
current mathematics. It's like it's hard to divorce times as we know it as an indicator of multiplication versus, especially in a mathematical concept, versus times we're literally saying this many times, not this times that, if that makes sense.
Yep. And so in this example, you can see there's 15 red shapes, right? So 15 is the product of 3 and 5 is what we're saying, which means that 3 is the quotient of 15 and 5. And also 5 is the quotient of 15 and 3. That's what it says in the definition. If one number is the product of two others, then each of the two is said to be the quotient of the product and the other. Anything to add, Chris or Kathy, or should I move on?
I think I'm good.
Okay. I'm stuck on the sum word in that definition. So if the definition of sum is the multitude of two disjoint sets, so if I always wonder if I can take out the word and put the definition of that word in the sentence,
Mm-hmm.
if it makes sense.
So the sum.
Is there any union going on with this definition?
Yeah. So here, I'll like break this out then. So to get the product, so the product of two numbers. So our two numbers are 3 and 5. 3 being the multitude of any given triad, and 5 being the multitude of any given pentad. Yeah. Um, I don't know if using the shapes is hurting. If maybe we want to use just dots. So so the numbers are multitudes, right? And so for us to get the sum of two multitudes, we don't involve the multitudes, we involve the sets that form them.
Can I try drawing something, Chris, on paper and showing it to the screen?
Yeah.
Okay. Kathy asked a question. She's asking where are the unions? Okay. So here I have 5 triads. Okay. So that would be 3 5 times, or 5 times 3, right? So the 5 triads, I can make a union of those. And the union would be the sum of those 5 sets. So that union is the set that we're using to define the product.
Okay.
So there's 5 3s that we add together. We add a 3 plus a 3 plus a 3 plus a 3 plus a 3, and we get a 15 by taking the union of those 5 triads.
Yes, that does make sense.
Is the union of 5 triads gives you a 15 ad, and that becomes 15 becomes a product of 3 and 5.
Is there any way you can expand then on the first seconds or the first of the second and how that connects to the definition that you just gave? Because that
Yes, I can.
definition you gave makes sense. How does
So
that connect to the first?
the product of two numbers, the first and the second. So the first number in this case is 5. I'm trying to say it's the first seconds or the first of the second. Okay. We're saying it's the sum of 5 3s. The first is 5. The sum of the first 5 of the seconds, 3s. So it's the sum of 5 3s.
Oh,
Take a
okay.
3 plus a 3 plus a 3 plus a 3. It's like repeated addition, and you do it to itself 5 times to get the product, is what we mean by it's 3 5 times or 5 times 3. See, 1 time, second time, a third time, a fourth time, a fifth time, 5 times 3.
I think the first of the seconds makes me think that it is the leading second
Yeah. Yeah. Yep.
rather
That's what
than the second number of times.
So it's
I
like
don't
you're
know.
taking 3. It's the first of the second.
Oh,
It's the first set of the second, I guess.
right. As opposed to the first number in the sentence, right?
Right. Right.
Yeah, there's probably better ways to define this. I was trying to be consistent with how I've used language before because the first and the second, that shows up a lot in these works. And it's always referring to the first time you say something, the second time you say something, like the antecedent consequent type of thing. Yeah.
Hit the wrong button
Okay.
there.
Feel free to contact the author if you have a better way of writing these definitions down. Okay. Can we keep going?
Yep.
Okay, I've got 2 definitions left. This one is 9th. A non-empty set is said to be finite if its multitude is a number. I repeat, a non-empty set is said to be finite if its multitude is a number. I can think of a set whose multitude is not a number. So that set would not be finite, it would be infinite. Infinite being the antonym of finite. So in order for it to be called finite, its multitude has to be a number. Does that make sense?
Kind of.
So there are non-numeric multitudes. is what this acknowledges. I guess this does raise the question, how do we det okay. I was gonna say, how do we determine that a set's multitude is a number, how that is evaluated,
With the definition of a number,
which is one or
the
the
sum of
sum
one and
of
a number.
one and a
Yeah,
number.
yeah. So the obvious example would be, think of the set that describes all numbers. That's not a finite set. That's an infinite set because its multitude is not a number. If you try to tack a number onto it, you could always add one more to it, and suddenly it's not the set anymore.
I think what the word I'm getting stuck on is non-empty. I'm not sure what that definition means.
I got you. So a set is said to be empty if it describes nothing. I think the example we used back in book 1 was the set that describes all elephants that can fly. That's an empty set. That set is neither finite nor infinite. So we just kind of exclude it from the definition because we don't know if it's finite or infinite. It's kind of neither. So what we're saying is that sets being finite or non-finite only apply to sets that are non-empty. So you have to have a set of things before you can determine whether it's finite or infinite.
Have we, apart from today, have we said non-empty at all? I know we've said empty, but we haven't, I mean, specifically defined non-empty. You're saying that just from understanding what empty means, we should then understand what non-empty means.
That's a great question. And that comes back to my math background. I keep like these words I use, like even infinite, right? Or disjoint that came up earlier, or non-empty, like your that's so ingrained into my brain as a mathematician because we use that word all the time. But non-empty is just a mathematician's trying to sound smart, right? Because it really just means it's not empty, literally not empty. So it's the
So then I would say it's full. I'm just teasing, but if it's not empty, it has something.
it has something.
What
Yeah,
is that thing that it has? It's almost like a
anything.
double negative.
It is a double negative. That's how mathematicians talk, and I'm sorry. But yeah, so I guess it could say like a set that has at least something in it, right?
Yeah.
As opposed to a non-empty set, or a set that isn't empty is said to be finite, right? That's another way to say it. But again,
Which
mathematicians do this all the time. They think they sound smart. We think we sound smart, right?
I'm sure it is smart. I'm just
a non-empty
Oh,
set. It's so common that I don't even think twice about it. Yeah.
do we even need to specify that it's not empty?
Yes.
Because if its multitude is a number, it has to be non-empty, right?
Well,
Because it's
in
the
my
sum of one and a number.
so a set says to be finite if its multitude is a number.
It's not possible for the set to be empty if its multitude is a number.
Um, yeah, I think you're right, actually. We don't even need that word, do we? A set is said to be finite if its multitude is a number. But then we're saying no, that doesn't work because then we're saying an empty set is not finite. And it's not that it's not finite, because not finite is the same thing as saying it's infinite. And we don't want to say that an empty set is infinite. So we just say it's undefined. It's not defined for empty sets. That's the reason it's there.
Well, it still wouldn't be defined, right? If we left it off.
Um,
Or maybe I'm not following.
no, because if you leave the word out, then you're saying that every set is either finite or it's not finite, right? But not finite is another way of saying infinite, right? It's an antonym because otherwise we're saying that every set is either finite or infinite if we leave that phrase out. But an empty set is kind of neither.
I see.
So it's
No, that
under.
makes sense. I see. I
Yeah.
see. We only deal with finiteness for non-empty sets.
Yes.
And the way we determine if a non-empty set is finite is if it's a number.
Yeah. And the
If
reason for
it's
that is because we have no other way of defining what it means for something to be infinite. Even the word infinite just means it's not finite, right? Like otherwise, how do you define infinite? It can't be defined. So this kind of narrows it down to any set that's not empty, that's not finite. We're just going to call it infinite.
That makes sense.
Yeah. Okay. 10th, a non-empty set is said to be countable if it is either finite or equinumerous with the set that describes all numbers. This definition is very famous. Georg Cantor, the one who invented set theory in order to deal with this particular question of what it means for a set to be countable. Because he postulated, or he hypothesized that there's different degrees of infinity. There's countably infinite, and there's also uncountably infinite, which to a non-mathematician seems like nonsense. Infinite is just infinite after all. But it can be proven that there are sets that are both countably infinite and uncountably infinite, according to this definition. For example, the set of all numbers, as we define them in this book, is a countably infinite set. The set of all odd numbers is also a countably infinite set, because both of those are equinumerous with the set that describes all numbers. An example of a set that's uncountably infinite would be a line. A line is an uncountably infinite set of points.
You can't ever say how many there are in a given section.
You cannot make a one-to-one correspondence. It's impossible to make a one-to-one correspondence between the points on a line and the set of all numbers. And that can be proven. Another example is the set of all real numbers, which we're going to call certa in the geometry series. We're not going to call them real numbers because they're not actually numbers according to this definition here in book 3. Okay? We've defined what a number is. Real numbers, quote unquote, is like I guess it's like an oxymoron. Those aren't actually numbers. Okay, and we'll talk about why as we get down to it. But if we do whatever you want to call them, whether they're real numbers or certa, let's call them the certa set. Okay, that's an uncountably infinite set, and that can be easily proven that it's uncountable. So therefore, there's more real numbers or certa than there are numbers, uncountably more. Did that make sense, Kathy?
Yes.
Okay. And to prove that, I'm sure Dale could come up really fast and do it. It's called a diagonal diagonal argument, which I don't want to do right now. But you could make a really quick argument as to why the set of real numbers is actually uncountably infinite. This question about the difference between countable and uncountable drove Georg Cantor to insanity because he wanted so bad to prove, I can't remember what his hypothesis was. But it took mathematicians beyond his lifetime to be able to solve some of these questions. So he didn't ever get to answer his question. But he wanted so bad to understand this idea of uncountably infinite that he actually went insane.
Wow.
Yeah, he's kind of obsessive like me. So I understand
Gotta
how
put
it
a warning on
feels
this video.
how it feels to have a question and you just have to answer it. I mean, that's kind of where these books came from, right? I had to know. And so I kept digging and kept digging, kept asking my students, back to what we were talking about at the beginning. I kept asking my students questions until I had my questions answered. And that's where the series comes from. It's answers to questions that I had that I asked my students as to what things are. I wanted my terms to be defined because I did not like what I was taught in high school. A whole bunch of procedures with nothing defined. The first time I discovered that the real numbers even had a definition when I was in college was like a huge moment for me when I said, what are the real numbers? And I found an answer to that question. And so continuing the search led me to putting all these series together so that we have definitions for everything, all coming back to how mathematics can be described through language. Chris, do you want to say anything to that?
I guess what's on my mind right now is it's so odd, but I feel like a lot of mathematical knowledge is kind of gate kept right now. Like, apart from my interactions with you, I would not have known where to go and seek out this type of mathematical knowledge. Like aside from, I don't know, maybe that's just because I am the age I am and libraries are on the decline, as I was growing up. Um, but I feel like when I even still think about mathematics like this, I jump to like Greece and Rome and those thinkers kind of tackling these things. I never really heard anything about mathematical research or development like happening past those time periods in school. Like everything you've talked about tonight, 19th century type things, like I never heard a lick of it, in school outside of like my connection to you. And I don't think anyone else really has either, unless you're actually like pursuing mathematics in very high education.
Mhm.
And
I
that's just
would
a little
love
weird to me.
I would love to invite Agnes Tushka, who I talked to today. I talked to you guys about before the video. Invite her to watch this because she says she wants to get into this discussion and just talk about exactly like you said. So, Agnes, if you're watching this, we want you on here. Is there a gatekeeping process to keep people from understanding these things? Um, and Agnes, can you see what I'm trying to say about rooting our mathematics in language and why that's so important for our children? So that they can articulate, like Chris said at the beginning so well, we're articulating what the world is around us, right? As opposed to just doing procedural mathematics. I mean, that's important to me. It was so important to me that I asked the questions until I had the answers. And fortunately, I had the right people, the right books, and the right context to kind of put together. But it was a lot of work. And I could not have done it without University High School, that's for sure. People like Chris and others that were willing to listen and to think with me and to ask the same questions. So the teacher became the student, as a good teacher should, right?
Mhm.
To be learning along with the students, lifelong learners. But yeah, these things are important to me because I want to know. I have to know what is a number. What are these things? That's just how I'm geared. And so my heart's desire is to share these things with people, especially if they're not mathematicians, because we talked about this before, Chris, also. They don't have the baggage that blocks them from understanding what I'm even talking about, right? It just kind of goes over their head because their understanding is locked in a certain way. And it took me a lot of work to unlearn everything I learned. So much work for those 7 or 8 years of university high school when I knew you, Chris, to get myself to be able to even step outside the box enough to find answers that were different than what I heard before.
I think
Yep.
I think that's the big thing. Up until I took your class, and I'm sure this is the experience of pretty much any student learning math, like in America and probably worldwide. Mathematics, as it's taught in the classroom, is presented as like done and absolute, and math is math.
Yeah.
And we don't test math in the classroom. We just are shown how to use it as it is. Like math went from this unshakable, absolute, completely charted out thing to something that was more like fragile and demands more scrutiny, like going into your class. Like there's just all this context that's just absent in the classroom. And that's kind of the historical bit. Like math has always been shifting and evolving and improving, like, and still is today. But there's no mention of that in most classrooms, not in my experience at least. It was kind of like, yeah, we figured it out at some point after Greece and Rome, and this is what it is now, and this is how you use it, and you just need to know how to use it.
Again, sorry to say this again, but Agnes Tushka is actually the closest person I've found in my career that understands the shiftiness of mathematics and the necessity of thinking and exploring. So I'd love to have her on this at some point just to talk. I'd love for you
That'd
guys
be
to meet her.
fantastic.
Love for you guys to meet her too. So I'll let her know that we talked about her tonight.
All right. Well, thank you both so much for the third, and we hope that others will enjoy it. And we'll have the resources attached in the comments or somehow for them so they can be able to see the book the third.
Okay,
All right.
sounds good. Kathy, thanks for your time. I appreciate it.
Yes.
Thank
Thank
you.
you, Daniel. Thank you, Chris.
All right, take care, guys.
Take care.